Hi everyone, I am Dr.S.SURYA, Assistant Professor of Chemistry, A.D.M. College for Women Autonomous, Nagapattinam. Today we are going to NMR spectroscopy. What is NMR spectroscopy? NMR spectroscopy is abbreviated as Nuclear Magnetic Resonance Spectroscopy. Nuclear Magnetic Resonance Spectroscopy is the study of molecules by recording the interaction of radio frequency, electromagnetic radiation with the nuclei of molecules placed in a strong magnetic field. The basis of NMR spectroscopy, nuclear magnetic resonance was first detected experimentally at the end of 1945, nearly concurrently with the work groups Felix Bloch and Stanford University and Edward Purcell, Harvard University. The first NMR spectrum was first published in the same issue of the Physical Review in January 1946. Bloch and Purcell were jointly awarded in the 1952 Nobel Prize in Physics for their research of nuclear magnetic resonance spectroscopy. The nuclear magnetic resonance spectroscopy is a crucial analytical tool for organic chemists. The research in the organic lab has been significantly improved with the aid of the NMR. Not only can it provide information on the structure of the molecule, it can also determine the content and purity of the sample. Proton NMR is one of the most widely used in NMR method by organic chemists. The proton present in a molecule will behave differently depending on the surrounding chemical environment, making it possible to illustrate their structure. NMR spectroscopy principle: many nuclei have spin and all nuclei are electrically charged according to the NMR principle. An energy transfer from the base energy to a higher energy level is achievable when an external magnetic field is applied. All nuclei are electrically charged and many have spin. Transfer of energy is possible from base energy to higher energy level when an external magnetic field is applied. The transfer of energy occurs at a wavelength that coincides with the radio frequency. Also, energy is emitted at the same frequency when the spin comes back to its base level. Therefore, by measuring the signal which matches this transfer, the processing of NMR spectrum for the concerned nucleus is yielded. The phase the sample is a magnetic field. Excite the nucleus sample in the nuclear magnetic resonance with the help of radio waves to produce NMR signal in NMR spectroscopy working. These NMR signals are detected with a sensitive radio receiver. The resonance frequency of an atom in a molecule is changed by the intermolecular magnetic field surrounding it. This gives details of molecules, individual functional group and its electronic structure. The nuclear magnetic resonance spectroscopy is a conclusive method of identifying monomolecular organic compound. This method provides detail of the reaction state, structure and chemical environment and dynamics of a molecule. The chemical shift in NMR spectroscopy. A spinning charge generates a magnetic field that results in a magnetic moment proportional to the spin. In the presence of an external magnetic field, two spin states exist. One spin up and one spin down, where one aligns with the magnetic field and the other opposite to it. The chemical shift is characterized as the difference between the resonant frequency of a spinning proton and the signal of the reference molecule. The nuclear magnetic resonance, the chemical change is one of the most important property usable for the molecular structure determination. There are also different nuclei that can be detected by NMR spectroscopy. H1 NMR and C13 NMR and 15 nitrogen NMR and 19 fluorine NMR among many more. The hydrogen NMR and C13 NMR are the most widely used in NMR spectrum. The definition of hydrogen NMR as it is very descriptive of the spectroscopy of the NMR. Both the nerds have a good charge and are constantly revolving like a cloud. Though mechanics, we learned that a charge in a motion produces a magnetic field. In NMR, when we reach the radio frequency radiation nucleus, it causes the nucleus and its magnetic field to turn. NMR spectroscopy instrumentation. The instrument consists of 9 major parts. There are discussed below: sample holder, magnetic coils and permanent magnet and sweep generator And radio frequency transmitter, radio frequency RF detector and recorder and read out the system. The sample holder occurs, it is a glass tube which is 8.5 centimeter long and 0.3 centimeter in diameter. Then magnetic coil is magnetic coil generate the magnetic field whenever current flows through it. Then permanent magnet, it helps to in providing a homogeneous magnetic field at 60 to 100 megahertz. Then sweep generator modifying the strength of the magnetic field which is already applied. The radio frequency transmitter produces a powerful but short pulse of the radio waves. Then radio frequency, it helps in detecting receiver radio frequency, and detector, it helps in determining unabsorbed radio frequency. Then recorder, it is NMR signal which are received by the RF recorder. Then read out the system is a computerized that record the data. The NMR spectroscopy technique, resonance frequency, it refers to the energy of the absorption and the intensity of the signal that is proportional to the strength of a magnetic field. In our active nuclei absorb electromagnetic radiation at a frequency characteristic of the isotope when placed in a magnetic field. Then the spectra upon excitation of the sample with the radio frequency pulse, a nuclear magnetic resonance response is obtained. It is a very weak signal and requires sensitive radio receiver to pick up. Then application, NMR spectroscopy is a spectroscopy technique used by chemists and biochemists to investigate the property of organic molecule. Although it is applicable to any kind of sample that contain nuclei possessing spin. For example, the NMR can quantitatively analyze mixture containing known compound. NMR can either be used to match against spectral libraries or to infer the basic structure directly for the unknown compound. Once the basic structure is known, the NMR can be used to determine the molecular conformation in solution as well as the studying physical property at the molecular level such as conformational exchange, phase change and solubility and diffusion. The chemical shift. In NMR spectroscopy, a chemical shift refers to the difference in resonance frequency of a nucleus in the molecule compared to the reference standard measured in parts per million ppm. It provides information about the chemical environment of the nucleus, particularly its shielding or de-shielding from the external magnetic field. The factor influence the chemical shift: electron density, electronegativity of neighboring atom and anisotropic effect. The electron density is a higher electron density around a nucleus provide more shielding, resulting in an upfield, that means lower ppm value. Then electronegativity of neighboring atoms, they withdraw the electron density, de-shielding the nucleus and causing a downfield shift, that means higher ppm value. The anisotropic effect in certain molecular geometries can induce local magnetic field that affect the chemical shift. An example, methyl halides. In proton NMR, the chemical shift of methyl proton increases in the order of iodine, bromine, chlorine and fluorine from 2.16 ppm to 4.26 ppm. This is due to the increasing electronegativity of the halogen atom, which de-shield of the proton. Then benzene, proton in benzene resonate downfield around 7.27 ppm. In proton NMR, due to the ring current effect, where circulating the electrons create a magnetic field that opposes the external field, de-shielding the proton. The shielding and de-shielding in NMR spectroscopy refer to the effect of electron density around a nucleus on the magnetic field in the experience. This shielding occurs when electrons create a magnetic field that opposes the applied magnetic field, effectively reducing the field held by the nucleus. De-shielding happens when the induced magnetic field reinforces the external field, making the nucleus experience a stronger field. The shielding mechanism, the electrons surround the nucleus are constantly moving, generating their own magnetic field. This induced field can oppose the external magnetic field applied to the sample. An effect of the nucleus is experiencing a weaker magnetic field due to the opposing induced field leading to shielding. Then the result, The shielded nuclei require a lower frequency to achieve resonance in NMR experiment and appear upfield on the spectrum closer to the reference signal. Then de-shielding mechanism. If the induced magnetic field reinforces the external magnetic field, the nucleus experiences a stronger magnetic field, and the effect this happens when electron density around the nucleus is reduced. For example, by the presence of electronegative atom that withdraw the electron. The result of de-shield nuclei require a higher frequency to achieve resonance and appear downfield on the spectrum. For the example of de-shielding, the anisotropic effect of shielding and de-shielding. The shielding proton in methane are shielded because in the carbon atom is more electronegative than hydrogen and pulls the electron density towards itself, creating the shield around the hydrogen nuclei. The de-shielding proton attached to one electronegative atom like chlorine, chloroform are de-shielded because the electronegative atom pulls electron density away from the proton, making it experience a stronger magnetic field. The shielding and de-shielding are crucial concepts in NMR spectroscopy that explain why different proton in molecular resonance at different frequency. The electron density around the nucleus, whether it is shielded or de-shielded, which turn in affects any chemical shift in the NMR spectrum. In NMR spectroscopy, an ABC system represents two nuclei that are strongly coupled, meaning their chemical shift difference is comparable to the coupling constant. This leads to a second order spectrum where the simple n+1 splitting rule don't apply, and the spectrum exhibit a disordered doublet pattern with enhanced inner line and reduced outer line. The first order versus second order spectra. First order spectra occur when chemical shift difference between the two coupled nuclei is much larger than the coupling constant. That means the spectrum shows a simple splitting pattern following the n+1 rule. Example, doublet and triplet, etc. Then second order spectra occur when the chemical shift difference between the two coupled nuclei is comparable to the or smaller than the coupling constant. That means the splitting pattern becomes disordered, and the simple n+1 rule is not applicable for the second order spectra. The AB system characterization: strong coupling, disordered doublet, and not easily impredictable. The first order coupling, the key features of the AB system is a strong coupling between the two nuclei A and B, meaning their chemical shift difference is similar to their coupling constant J. The distorted doublet, the doublet in the spectrum are not of equal intensity. The inner line closer to the outer other nuclear signal are enhanced, while the outer line are diminished, creating a roofing effect, not easily impredictable. The distorted pattern make it challenging to directly read off the coupling constant and the chemical shift. Specialized analysis technique are needed to extract these parameters. The examples: consider two protons in a molecule where the difference in the chemical shift is similar to the coupling constant between them. The system would be an AB system. Instead of seeing two distinct, equally intense doublet as in a first order AX system, you would observe a pair of distorted doublet with the inner peak being a more intense. In AB spin system, in NMR spectroscopy, represent a pair of strongly coupled nuclei, leading to second order spectral characteristic with a distorted doublet and the absence of simple first order splitting pattern. The complex of NMR spectra with spin-spin interaction can be simplified using technique like double resonance, which eliminate a coupling between nuclei by using a second radiation to flip the spin of one nucleus, thus simplifying the spectrum. Other methods include isotope exchange, high field strength, and 2D NMR techniques is used as such. Explanation: the spin-spin coupling. The interaction between neighboring NMR active nuclei causes splitting of spectral lines, leading to complex patterns. The double resonance technique involves irradiation of the sample with the second radio frequency field while observing the NMR spectrum. This Second RF field can be used to selectively flip the spin of the specific nucleus, effectively decoupling it from other nuclei and simplify the spectrum. The isotope exchange in replace the hydrogen atom with deuterium, the heavy hydrogen atom example, can remove spin-spin coupling as deuterium has a different nuclear spin than hydrogen. Then high field strength using high magnetic field strength can lead to better resolution and separation of peak, making it easier to interpret the complex spectra. Thank you.